Hi everyone, thanks so much for joining me today. So today we are going to have a long day. I'll just show the schedule once again so that you guys are aware of all the breaks and the schedule for the day, the agenda for today. But the broad topic that we'll be discussing today is about how to interpret or explain machine learning models, right? So the schedule for today is the following. So we are going to break it down into like 4 parts or 4 sessions. From 9 to 10:20 a.m. we are going to do a brief intro, discuss a little bit about why do we even need to care about interpretability, or should we care about it, or are there scenarios where we need to care about it and others where we do not need to care about it. And then I'll give a quick overview of inherently interpretable models. And don't worry if you're not completely sure what that means, we'll get to that. From 10:20 to 10:40 we'll do a 20-minute break. From 10:40 to 12 we'll have the second part, which will be focusing on post-hoc explanation methods. From 12 to 1 we'll have lunch. We'll give a 5 minutes of settle-in time from 1 to 1:05. So from 1:05 to 1:25 we'll do some breakout groups where you get to sort of discuss with other folks here about some questions before we get into the second half. And from 1:25 to 2:45 we'll do the third session on evaluating and empirically and theoretically analyzing model interpretations and explanations. So then we do a 15-minute break from 2:45 to 3, and then from 3 to 4 we basically continue the discussion on our empirical and theoretical analysis and conclude with some future research directions. Okay, so this is the agenda. So feel free to kind of pick and choose the things that would be most useful for you and so on. But this is a high-level overview. Does that sound good? Okay, awesome. All right, so with that, let's get into the initial bits of today's talk. So since we have the whole day today, we are going to ease in by talking a little bit about what exactly are we thinking about when we try to interpret machine learning models. Where can this be useful? When can it not be useful, and so on, right? So I'm sure several of you are familiar with scenarios like these. For example, healthcare or criminal justice system or finance and so on, and also several other applications, like whether it is social networks like Facebook or Twitter, whether it's your online product shopping portals like Amazon or Goodreads, and many, many more. So why am I showing all these applications is because today machine learning is in all these applications. And of course, I don't need to tell you guys that because Stanford being the hub of machine learning, I'm sure you guys have encountered applications, read about research, been in touch with like companies which build apps for any of these applications, right? So they're all using machine learning. So given that that's the reality of today's world, now we want to ask, given the topic of this workshop, we want to ask, is model understanding needed in every such application? What do you guys think? So there are several such applications. Do we want to understand what machine learning models are doing in each of these settings? Or are there specific settings where they might be more helpful in order to sort of understand model predictions or model behavior? Any thoughts? Okay, yeah.
I think it would be more critical to understand the model in more safety critical systems, like medical settings or like criminal justice system, than just recommendation system.
Right, great. And why do you say that?
I think like the effect of the machine learning system on the individuals or like the system safety level is like more high stakes than like recommended system.
Yeah. Right, that's exactly right? So we may not want to understand, or at least, the emphasis or importance of understanding how machine learning models are behaving is probably much higher in settings like healthcare or criminal justice or like, loan approval decisions and these kinds of settings, because the decisions that we are making there are probably going to impact people's life, right? Their health and, their livelihood and so on. Whereas if Facebook, for example, recommends a wrong friend to you, you would, it's fine, like you would probably not be very pleased, but that's not the end of the world. You'll probably click a button there and move on, right? So that's exactly right, right? So first, I want to kind of start this discussion by saying, because this is a very hot topic of debate, whenever I give talks and do these discussions, it's like there are always audiences that come up and say, oh, but like we don't need interpretability here, right? So I want to kind of start with that up front, that not all applications require understanding of models and their predictions, right? So for example, as you rightly pointed out, things like ad or product or friend recommendations and so on, and also settings where there is no human intervention involved. So there is no human who is looking at a prediction and trying to make a final decision. So where there is no human intervention involved in the final decision making, in such applications, you may not really even need to think about model understanding, right? And why is that the case? Exactly because there are very few consequences to making incorrect predictions in these cases. Of course, if you make a lot of incorrect predictions, then a company might lose revenue and so on. But as long as, the number of incorrect predictions you're making are few, the consequences for those are like much lesser, right? And a lot of these problems, especially when we think about recommender systems like ad or movies or products and so on, these problems are extremely well studied. And a lot of systems or machine learning models that are built for these settings have already been extensively validated in real world applications, which means we can pretty much trust that these models are going to make accurate predictions, quote unquote, right? But again, as machine learning, the reason why XAI and in fact this whole research on trustworthy machine learning or emphasis on safety has become popular in the last few years is because of the increasing deployment of machine learning models in settings like healthcare or justice or financing and so on, right? And the nature of the decisions in these kinds of settings is that the decisions are often high stakes. And as you rightly pointed out, they impact human lives, their health, their finances. And the more important thing is a lot of these settings are relatively less well studied. And models that people are developing for these settings have not been extensively validated on these settings, right? So the combination of those two things is what is pushing people to consider interpretability or explainability or model understanding seriously. So what is the result of this kind of a setting? So we talked about the settings being high stakes, and we talked about the settings are relatively understudied. So what does that imply, right? That implies that accuracy, computing accuracy of a model is no longer enough. The reason is, a lot of times, since these settings are not very well studied, the train test data which you are using to build your model and test your model may not even be representative of the data that will be encountered once you deploy the model, right? So if that is the case, then accuracy numbers kind of become a bit meaningless, right? And apart from this, in these kinds of settings, a lot of auxiliary criteria are also critical. So for example, you need the models to be fair and not discriminate against minority groups. There is also legislation or laws or rules that are coming out which are actually trying to mandate right to explanation when models are being used to make critical decisions. And of course, there are safety criteria that also need to be accounted for when we develop these kinds of models, right? So accuracy alone is not enough anymore in these kinds of settings. Emphasis on other kind of criteria is also becoming very important. And the sort of both the interesting and the challenging thing is that these auxiliary criteria are often hard to quantify, right? So for example, I might be able to say that, oh, I want my model to be fair, right? But can I quantify it perfectly, completely? Maybe not, right? And the definition differs from setting to setting. Similarly, we want our models to fail safely. What does that mean? We are not always sure what that means. So in some sense, there is, the challenges associated with like completely quantifying these auxiliary criteria is also what puts the spotlight back on understanding machine learning models. right? So in some sense, the challenge of being hard to quantify is basically what comes out as incompleteness in problem formulation, which makes it harder to sort of quantify something and optimize for it right away, which is what typically as machine learning researchers, if there is a measurable quantity, we can always do, optimize for it, right? So we can always do something with it, optimize for it. But in this case, we are not completely sure how to even specify it. So there is incompleteness in this kind of problem formalization in these settings. So our solution to all this is, how about we try to understand the model behavior in different ways, shapes, and forms. And once we see it, we are probably going to know if there is a problem with it, either with safety or with fairness or any of the criteria that we care about, right? So just to summarize our discussion, when and why do we need model understanding? So model understanding becomes critical when, one, models are not extensively validated in real-world applications, and train and test data that we have are potentially not representative of real-time data. And the second reason why model understanding becomes critical is some of the key criteria that are required in your setting are hard to quantify, and we'll need some kind of a you will know it when you see it approach to figure out if there are any problems or things that violate those criteria, right? Is that good? Okay, are there any questions so far? Yeah.
So, could there be another setting where you might care about explainability, such as like you want to understand some data, maybe first like science or something like that. So you train a machine learning model and then you look at an explanation to just gain understanding. Is that do you see that as fitting in here as well, or is that a separate topic?
Yeah, no, that's a good question. So you're saying explanations as a way for augmenting our own knowledge, right? So that's definitely, I think a lot of this biomedical sciences uses explainability for that quite a bit. So I think it is kind of probably not touched upon here, but I would say two things about that. It's definitely an approach that is being followed, and I think it is perfectly useful. At the same time, I think we might also want to be a bit careful about sort of your model is learning this from the data. So you are taking all of that and trying to form human knowledge out of it. So what if there are some spurious things that are being picked up, right? So the reason why I'm not going into that track is I think it has a lot more. Once you open that Pandora's box, there is a lot more that would come out. But definitely, I mean, it's being used that way these days to sort of, because, models are kind of learning things that people may not know, and explanations are a way to transfer that knowledge. But how much of that knowledge should be transferred, how to figure out if what part of that knowledge is spurious, what part of that is valuable, I think there are some gray areas there which need to be thought through more, which unfortunately I'm not sure if it's happening enough. Sure. Okay. All right. Okay. So I'm going to keep going. So now that we have talked so much about when and why model understanding might be useful, I'm just going to show a few applications just to concretize all of this, right? And we'll use some nice, simple, fun pictures to see the different use cases in which explanations might be helpful or model interpretations might be helpful. You'll not only see the application, but you'll also see examples of what an explanation or interpretation could look like, right? So let's say that now we have a predictive model, so which takes as input some images, and then it makes predictions about the animal that's in the images, right? And this model was built by a developer. So you pass this image and then it's rightly predicting that this image is Siberian Husky. But if you sort of probe the model a little bit more and see what are the areas of the image that the model is focusing on, what you see is that the model is focusing on the snow pieces, right? So in some sense, while the prediction looks okay, once you see the features that the model is looking at or paying attention to, you see that it's actually not looking at the animal, but rather at the background or trying to find snow in the image, right? And that's what it is using to predict the image as Siberian Husky. So in some sense, this understanding is basically what tells the developers that, model is relying on spurious or incorrect features, and maybe we need to debug this model better, improve it, and so on. right? So here is a clear use case where model understanding is helping with debugging of models, which I'm sure several of us, whether researchers, engineers, scientists who use machine learning models, can find this incredibly valuable. Okay, so now let's look at another use case. So where there's a predictive model that is being used by a particular judicial facility to make decisions about if people should be released on bail or not, right? Again, I just want to put a disclaimer out there that I'm not advocating for any such applications, but unfortunately there already exist some of these out there. So, you know, the way we are thinking about it is we are basically trying to analyze that setting a bit more, okay? All right, so these kinds of models, they take the details of the defendant, like for example, the defendant's socioeconomic status, their demographic attributes, their past criminal history, and so on, and predict if the person should be released or not, or is the person too risky to be released or not. Right? So in this case, the model is taking the details of this defendant and making a prediction, but then this does not give any information to the judge about whether or when and how to use that prediction, whether they can rely on this prediction or not. Okay? But if we show the judge some of the key features that the model is focusing on, for example, maybe the model is looking at race and gender when making this prediction, the judge will realize that this prediction is basically biased. It's being based on features like race and gender, which should not happen. So the judge is going to hopefully discount such a prediction and make his own decision, right? So in this case, model understanding has helped facilitate bias detection. Okay? Similarly, in another scenario, now we can think about end users. So banks often have such models which they employ in order to sort of predict who should be given a loan, right? So loan applicants' details or their application will be passed on to the bank. The bank then runs their predictive model and determines if a person should get a loan or not. Now, let's say an applicant is denied a loan. If we just tell that person your loan is denied, sorry, that's it, that's not very helpful because now the person doesn't know what to do anymore, right? So they don't have a means for further action. But instead, if we actually tell them, increase your salary by say 5 or 10K or 50K, pay your credit card bills on time for say about 3 months, then come back and reapply and you'll get a loan, that is actionable information that the person can use in order to sort of work on their profile, come back and reapply. Right? So in fact, these kinds of mandations have been encoded in some of the legislations like GDPR, especially for the finance sector or banks, which are using predictive models in deciding on loan applications and other such things. So in this case, model understanding is helping provide recourse to individuals who are adversely affected by model predictions, right? And similarly, if we think of a healthcare scenario, so if there's a doctor that is relying on model predictions and the model is basically taking a bunch of data and labeling patients as like healthy or sick, now the doctor, again, if they just look at the predictions, they have no way of knowing which ones to rely on, which ones they should apply their own judgment to, and so on. But if we had like a full understanding of what the underlying model is potentially doing, so for example, in this case, if that's what the model is exactly doing and the doctor sees that, the doctor can quickly realize that the model is using irrelevant features like ID numbers when making predictions on female subpopulation, right? And therefore, they should not trust the model's predictions, at least for that subgroup. So in this case, model understanding is helping assess if and when to trust model predictions when making decisions, right? So such an understanding can in fact also be helpful for regulatory authorities in deciding if a model should be sort of approved for broader deployment or not. Right? So in this case, if an authority like FDA looks at that explanation of what the model is doing, the authority might realize that, okay, this model is just using irrelevant features on half the population, which is basically all the females, right? And so it's not ready for deployment at this point. So in this sense, model understanding can also allow us to vet models to determine if they're suitable for real-world deployment. Okay? So just to summarize, there is obviously a lot of utility to sort of understanding models and their predictions. For example, applications like debugging, bias detection, recourse, if and when to trust model predictions, vetting models to assess for suitability for deployment. All of these are like use cases or applications that are enabled by model understanding, and there are several stakeholders that benefit from this. Right? So including end users like ourselves who might apply for loans at banks, or decision makers like judges, doctors, policy makers, or regulatory agencies, or researchers, scientists, engineers. All of us can benefit from this in some way or the other. Okay, right? Any quick thoughts, questions, or we can move on? All right. Great. Okay, so now that we have discussed so much about where model understanding can be beneficial, when it may not be beneficial, and so on, let's take a step back and think about how can we actually achieve model understanding, right? So while there are several approaches to do this at a very high level, very broadly, you can think of two classes of strategies that are used to achieve model understanding. So one is build models that are inherently interpretable. Right? So for example, models like linear regressions, logistic regressions, or shallow decision trees, or like small rule-based models. So these are all models that are often considered as inherently interpretable because you can look at those set of rules, and as a human we can understand what the model is doing when making its predictions. Right? Of course, one could argue that if I give you a decision tree with like 100 levels, that's not interpretable anymore, right? So even within these classes of models, the models that are sparser, shallow, those are the ones that we can look at, read off a piece of paper, try to make some sense of them, okay? So that has been one popular approach that had been used like all the way from 70s, 80s, and like now has more renewed interest. So the second strategy that has become more popular in recent times is to explain pre-built models in a post-hoc fashion, right? So what do I mean by that? So you could have a black box model, you could have an extremely complex deep neural network model. So we can take such models and then pass it as inputs to our explainer algorithms, and they in turn will break these down into simpler models that we can understand. Right? So for example, you can take a whole, let's say a 200-layer deep neural network and then pass it through an explanation algorithm, and that algorithm can then sort of maybe give you important features associated with a particular prediction. Right? So these sort of approaches or class of approaches have become super popular in recent times, but have also been the subject of a lot of discussion and debate about their vulnerabilities, advantages, and so on. Okay, so let me just sort of throw it back to audience and see. So which approach do you think is preferable, or is there a reason why you would use some approach in one context and not the other? So out of these two approaches, building inherently interpretable models versus explaining pre-built models in a post-hoc fashion, which one do you prefer and why? Yeah.
So the first one seems kind of nice because if the model is inherently explainable, you don't have to do anything above that. But I think for the second one, that might be more applicable for like complex models.
Yep.
Especially like vision, for example, and then also the example of if you have a really complex task and you have like a tree algorithm, if it has like 1,000 decisions that are made, I wouldn't call that very explainable. So probably the second one for more complex tasks.
Yeah. So in some sense, what you just said can be summarized using graphs like this, right? So what we need to think about is this kind of a scenario of, are there trade-offs between interpretability and accuracy, right? So for example, if you're working with some data or in a setting where you can maybe build a 5-level tree and that has a very high accuracy, that's probably good enough, and the model is inherently interpretable, and it's also giving you accuracy and you're done, right? But in a lot of real world applications, as you rightly pointed out, the data is becoming more and more complex, more and more high dimensional and large. And at which point these kinds of trade-offs start kicking in more and more. Right? So in fact, for data sets in NLP, vision, and even some very large tabular data sets, biomedical data sets, these kinds of data, what you see is that the models that are often considered as inherently interpretable, like regressions or trees, they're much less accurate than models like random forest, which is an ensemble model, or deep neural network with several intermediate layers and so on, right? So as we are running into these situations where accuracy interpretability trade-offs exist, we are being kind of forced to choose post hoc explanations. Otherwise, we can just rely on inherently interpretable models, right? So what are these kinds of situations? So we just talked a little bit about, if your data is too complex, you might have to build a complex model for the sake of accuracy, then use post hoc explanations, right? So let's dig a little bit deeper, or at least give an example of when you might be able to use inherently interpretable models and when you might be able to use more complex models and hence rely on post hoc explanations, right? So here what you see is like a two-dimensional data set, obviously a very simple data set, a toy example, and the data is almost linearly separable, right? So you can essentially draw a line, fit a hyperplane, and essentially fit a linear model, and you'll be able to get a pretty good accuracy here. So in some sense, here is a setting where you can build an inherently interpretable model, and that will also be accurate, okay? So now in the other case, let's say if the data has decision boundaries which are highly curvy and non-linear, in those cases it would be hard to build a simple model and still have it to be accurate in terms of its predictions, right? So in that case, complex models might achieve higher accuracy and people might resort to using post hoc explanations if they want to explain such models. And beyond this, sometimes you just don't even have enough data to build a model from scratch. So which happens a lot in real world settings. So for example, if hospitals want to sort of try and deploy algorithms or models for scheduling doctors with patients or like predicting, incoming traffic on a day, a particular hospital might not even have enough data collected themselves to build such a model, and they just have to use somebody else's model to do it, right? So all they get is some kind of a proprietary black box, and they may not even really have access to it. So in such case, they just have a black box and they're stuck with post hoc explanations. Okay, so in summary, if you can build an inherently interpretable model, which is also adequately accurate for your setting, so that's the way to go, right? So because there is no other additional level of complexity or approximation there. But otherwise, in cases where this is not possible, post hoc explanations often come to the rescue. Okay, so with that, let's jump into the main pieces of today's talk, now that we have hopefully set the stage for all the initial pieces, laid out the motivation, gave you a high-level picture of what this field is about. So today we'll be discussing these 4 to 5 broad topics. So first we will dive into inherently interpretable models, as we just discussed. And next we'll get into post hoc explanation methods. Then we'll think about evaluations of these and interesting empirical and theoretical insights on these, and close with a discussion on the future research directions.